Welcome to Peninsula Seniors Out and About. We're at the Western Museum of Flight in Torrance. Let's go see what Cindy has for us today.
Welcome everyone to the Western Museum of Flight. I'm Cindy Maka, the director. We have all been hearing about the amazing developments in efficient delivery systems for both commercial and government-sponsored satellites. We are fortunate today to have as our celebrity guest speaker someone who is playing a major role in this exciting new segment of aerospace industry. Ladies and gentlemen, CEO of Virgin Orbit, Dan Hart.
Well, it's great to be with you today. Thanks, Cindy. Talking with some of you before we got started, I can see that around this group, we could build about any spaceship or aircraft that we wanted to with the talent in the room. I'm going to talk to you a little bit today about space, what's going on with satellites, the transformations taking place, and I'll talk to you about the systems that we're building down in Long Beach at Virgin Orbit. So I thought that I would start off a little bit about the company and the purpose of that, and then talk a little bit about sort of the history of spacecraft and how we've developed, and then look forward and take a look forward at what's coming up. So number one is Virgin Orbit is a company founded by Richard Branson, one of his two main space ventures. You've probably been following Virgin Galactic, which operates out of Mojave. That's focused on human space flight and suborbital space flight, and 2 weeks ago you would have seen them take flight on a powered flight and get quite high in altitude and get quite past Mach as they progress to commercial operations. From Virgin Galactic, Virgin Orbit was born about 14 months ago out of a project that's been taking place over the last 3 or 4 years, and that is focused on small satellite launch and air launch in particular. And so I'll talk a lot about Virgin Orbit and our role as looking forward. I'll just say that Richard really provides across his company's purpose, a sense of vision. Where Virgin Orbit is focused is really how we utilize space to bring good and progress here on Earth. And we'll talk more about that as we talk about the system. But first, let's sort of go back a little ways. You know, space, commercial space, military space really came to its initial childhood in the 1960s. And a few miles down the road, 1963, SYNCOM 2 was first launched and used to make initial experimental phone calls from through geosynchronous orbit, where John F. Kennedy was calling a prime minister in I think, Africa for the first, one of the first experiments and use of a global communication. And then SYNCOM 4, or SYNCOM, yeah, I think it was 4, in 1964 was launched and broadcasted the Tokyo Olympics, and now the whole world got to see a little bit about what can be done from space. Well, see, that was the very beginning, and of course SYNCOM was about this big and maybe about this high, and was put up by a Delta rocket. Pace forward a few years, over the last 60 years, and communication networks are everywhere. And most of them are plugged in at some point to, usually these days, a geosynchronous satellite, some satellites in other orbit, but primarily geosynchronous satellites which are hovering over the Earth, where our credit card information flows, where our, obviously our internet information flows. We're also darn used to now, after 60 years of satellite communication, just instant communication. My kids, if the video doesn't show up within a second or two, there's clearly something wrong with the Wi-Fi. Communication, navigation, of course, we now can't walk more than about 150 yards without looking and seeing where our GPS location is. I've had the honor to participate in that program from both the launch and satellite side, and it's really tremendous. Seeing, you don't get the, when I was a kid, it was, well, I was on this corner, and you were on that corner. So that doesn't happen anymore. Of course, imagery from space is changing economies, whether it's counting cars in parking lots or looking at crops and understanding fertilization patterns and moisture patterns, weather, emergency weather. It's changing our life everywhere. Space is a part of many, many, many facets of our life and has really grown up over the last 60 years. Earth science and understanding our environment and how it's changing and what to do and where we have opportunities. And of course, in the defense side, I mean, we don't operate military campaigns without space. It is the ultimate high ground, as General Goldfein said at Space Symposium this week. We don't operate our aircraft, our ground troops, our navies without coordinating through command and control and intelligence that we get from space. So space has certainly become a mainstay, a major structural element in the fabric of how we live every day. But as we've grown up in space, we've also limited ourselves in many ways. And space has been a very, very expensive venture historically. 20 years ago or 10 years ago or maybe even 5 years ago, putting a capability in space meant spending $200–300 million on a satellite and $100 million or more, $150 million, $200 million on a launch vehicle. And that's just to get started. And then you have to support and operate it over 10, 15 years. So has been a very, very expensive proposition. And because of that, it's typically been focused on areas where there's a lot of money. And from that, we've grown up what they call the digital divide, where resources and communication resources, imaging resources, most space resources that typically have operated from geosynchronous orbit have been placed on areas with patterns that can give advantage to areas like this, areas where there's a fair amount of money, a fair amount of traffic, and a fairly modern communication capability. And other areas of the world have less. And so it's kind of an interesting and unfortunate turn of events that both limit communities but also limit the possibilities of the global economy, because not everybody is playing in the same way. And then there's other facets that the tight communities of space have also sort of been associated with. There are very few governments that have capabilities in space. Of course, the United States has been a leader, will continue to be a leader. And then businesses, because of a $500 million investment, there are very few ideas that actually pass the hurdle rate to be able to start up and operate and gain enough revenue to pay for the capital in space. Well, all that's about to change. And what we're seeing is an activity going on in space that is busting open these barriers that have traditionally been there. And it's an incredibly exciting time, and it's a time of transformation. And it's a focus that has grabbed the imagination of a lot of entrepreneurs. It's a focus that has grabbed the attention of Virgin and Richard Branson, and it's really part of the fundamental purpose of Virgin Orbit. So let's talk a little bit about satellites and where they've come from and where they're going. And so SYNCOM went up in the 60s, and after that we spent a lot of time studying the environment of space. And over the following 20, 30 years, we became pretty damn adept at designing electronics, designing structures, designing materials that could withstand the environment of space. And we became very proud that our satellites could last not only 7 years, but maybe 10 years, or 12 years, or 15 years. I mean, heck, we've had satellites in orbit lasting 25 years. And it's really a statement. It's a credit to the designers, to the engineers and the technicians and the operators who worked on these satellites that they did that. And then an evolution started to happen where businesses who were operating satellites, and there were only a few large operators over the early 30 years of space, as well as the military, started to realize, the business is kind of changing over a 20-year period. And the resources that I once needed just over here, I need over here now too. And a satellite that lasts 20 years, having flexibility in that satellite would be beneficial. And so companies across the world started to work in flexibility and reprogrammability, and maybe some added propellant so you could move it around. And flexibility in the first generation was all about how you could make use of these long-lasting satellites and have them morph here and there. And there's been a huge amount of wonderful work done over the last numbers of years of programmable satellites. So beam patterns can be moved. In some ways, in some areas, even spectrum can be reallocated to different satellites. But they're still large satellites, typically, that are up there for long periods of time. And the government, the same thing. The threat changes, the hotspots in the world change, and they need that flexibility as well. And that's grown up as satellite technology has grown up. That was the first generation of flexibility, I would say, for satellites. And all along, as we did that, a lot of other ideas were percolating about, gosh, could we have higher responsiveness? Could you have satellites in storage or something and get them up quickly if you needed to? Could you get a quicker refresh? But what's happened historically is the cost of launch and building new satellites were pretty huge. So you were better off making use of the assets that you already had in orbit. Well, that's all changing. And what's happening is satellites, and I've got this picture of a school bus and with solar arrays on it. You don't usually see those driving around. And a microwave with solar arrays. And so what's happening is a lot of the capabilities that once required a satellite the size of a school bus can now be packaged in a satellite the size of a microwave, or in some cases a washing machine, in some cases a toaster, or other appliances. And what's driving that is, number one is Moore's Law. Electronics, both the density, the low power aspect so that you can package it and actually have a satellite that's not 900 degrees Fahrenheit, because of power, but is actually nice and cool and operating in space, has grown enormously. Just like your cell phones were used to, they used to be big devices hanging on the wall. Now they're these little cell phones that have so many functions. Every once in a while you might talk in one. But incredible devices. And what's happened from a flexibility standpoint is people are realizing, I spend money on supporting an asset in space, I would like it to have the highest technology. And so there's a theme that's growing that, I don't necessarily want to have a satellite that's lasting 15 years. I'd rather it last a little shorter time and then put a new one up with the latest technology and beat my competition. Or if you're the military, understand how the threats are evolving, get the latest technology, and adapt to the threats. And so, raise your hand if you're using a cell phone that's more than 10 or 15 years old. Okay, well, we have a couple. Most of you don't. Most of you kind of are tired of waiting for the software to run and getting the latest apps. But for a while I was using a flip phone also. I thought they were kind of cool. But Moore's Law is a huge driver. And then there's other technologies that are really driving this as well on the satellite side. Electric propulsion has really grown up and matured to where it's a huge driver. So no longer do you have to have chemical propulsion. The ISP, or the efficiency of the engine, grows significantly, and so you can package a satellite with a lot less volume for the propellant. Phased array technology, other communication technology like laser communications, getting communications, these big antennas, into small form factors. You can communicate from Mars to Earth with a small package about this big. using laser communications. So, all these ideas, all these technologies are growing up, and so satellites are becoming smaller and smaller. And that is changing the economy in space. And there's a huge transformation taking place around that. And what's happening is companies are growing up around the idea of satellites that are 1/10, 1/20th maybe, the cost of the historical large satellites. Less than that, maybe in some cases 1/100th, which lowers the bar to be able to put some capability into space. If everybody here, I'm sure, is familiar and takes a lot of pictures with your cell phones or your cameras, the capability of optics and cameras and the electronics that support those are enabling companies like Planet and others who can operate with very small satellites and take meaningful pictures of the Earth, and so we can understand what's going on around there. And so what we see is a huge amount of capital coming into the market of companies now who are realizing they don't have to spend $500 million to get started, but can get started with maybe $20 million, $30 million, prove out a concept, and then build on it, and put up small, medium-sized, or in some cases very, very, very large constellations in low Earth orbit. And so there's a lot of mix there going on, a lot of discussions on Earth observations that I mentioned, communications and networks, both to communicate terrestrially, so that we have more options to communicate with each other, and also companies are growing up with their antennas pointed the other way in how they can help supply infrastructure for large geosynchronous satellites. And so there's a whole infrastructure being developed in space with these new technologies and new capabilities. And I'll stop there for a minute because I don't want to lead anybody to believe that, well, everything's leaving geosynchronous orbit and going to move to low Earth orbit, and we're not going to anymore have our large satellites, because we will always have large satellites parked in these great parking spots that sit in the same place relative to the Earth night and day and support us. But we've got a whole new diversity setting up of smaller satellites in medium orbit and low Earth orbit. And just to give you an idea, for those of you who aren't space-oriented, low Earth orbit, it typically is anywhere from 300 to 1,200 or so kilometers above Earth. Geosynchronous is, and I'm going to switch units, sorry guys, is about 22,000 miles, and MEO is right between there. And so that gives you an idea of the distance. So if you're in low Earth orbit, for instance, that's typically where you do your Earth observation, because you're closer, you get a better picture. Typically, communications has been done from geosynchronous orbit because you're always there relative to the user in one place. But technology has allowed us to move past that. If we look at the latest studies, and I've got the Euroconsult study sort of referenced on the chart, the amount of activity forecast with all the amount of capital coming in from private investors over the next 10 years, they're predicting about 6,000 small satellites being put into orbit. A huge amount. Now the next thing you're going to say is, well, how are we going to manage all that? And the Secretary of Commerce this past week announced that the Commerce Department, actually the Vice President announced on Monday that the Secretary of Commerce would take on space traffic management, and then Secretary Ross made a speech about a couple of days ago to talk about what the plans are there. But there is an infrastructure that we have to catch up with, just like we did in maritime about 200-300 years ago, just like we did in air a whole lot more recently. We need to have a whole situational awareness set of sensors so that we understand what's going on in space, and then there'll need to be some enforcement on behaviors in space and norms, and that's a whole area of exciting development for space. So I'll tell you a little bit about what we're doing at Virgin Orbit now. So there's all these small satellites being developed. And typically, or traditionally, these satellites went as back passengers with large satellites. So if you were putting up a big communications satellite or you were putting up supplied a space station, let's say, you could tag along on a ring behind the satellite, and you could bolt your satellite, and after the main package was delivered to orbit, the small satellite would be set free. And it's a pretty efficient way to get to orbit in terms of cost, because you're not paying for most of the ride. You're just a passenger in the glove compartment. And that works for experiments very well. It doesn't work that well if you have to get somewhere to a specific orbit at a specific time. And so as these companies and missions are growing up with small satellites, they're becoming demanding customers. They have their own revenue stream that they have commitments to feed, and they don't want to spend all of their spacecraft life drifting over from space station orbit, let's say, to their operational orbit. They want to get to where they're going to get to when they need to. And so these spacecraft are just screaming for dedicated service at the right size to get them to orbit. And of course, you can't effectively, if somebody's got a couple of small satellites, they're not going to pay for a large rocket to get them there. So enter Launcher 1. Launcher 1 is an air-launched system. We come under the wing of a 747 aircraft, and we take up a small rocket. We drop it at about 35,000 feet, and then the rocket takes the 300 to 500 kilograms up to low Earth orbit. If you ever drive by Long Beach Airport, you'll see our aircraft we call Cosmic Girl sitting on the runway or the taxiway next to the runway at Long Beach Airport. So she's a very efficient aircraft and launch system. So the idea behind the system is this. We have our aircraft, you can see in the middle, modified 747-400, modified to be able to carry a 60,000-pound rocket under the left wing. And if you're familiar with the 747 aircraft, you know that the aircraft was designed to carry or ferry a fifth engine. And so it was done so if you ever have a situation remotely where an aircraft is stranded, or you just need to rebalance your inventory, you can carry an aircraft over there. And so we've modified that location to carry our rocket. And we've built a pylon that'll release the rocket once we get up to altitude. So we have in the middle the most reusable initial stage on a launch system ever created. Boeing 747 aircraft with all the operability that's built into that aircraft, all the supportability, all the great ground equipment, understanding, knowledge, and we have a wonderful crew that supports her and pilots that fly her. And so once we getting up to altitude with the 747 give us a nice advantage, then we have as simple a rocket as we can make. And so what we've done is we've taken state-of-the-art technology and we've applied it to a two-stage rocket to get small satellites to orbit. So the rocket is all composite material built up in our factory in Long Beach by the airport. It's a single engine for each stage, LOX kerosene, a very well understood propellant that's been used in rocketry since the beginning. We use what's called a pintle injector. With those of you who know rocket engines, it's basically the same technology that landed us on the moon. And so it's been around for a while. And then we take modern manufacturing techniques, both in composite construction of the structure, as well as things like the engine, which is designed and built down in Long Beach. We're using advanced manufacturing like additive manufacturing, simplifying some of the alloys that we use in engines to build as simple and as robust and as manufacturable engine as we can. Because we fly away from an airport and not out of a launch base, we can get away from the range and some of the coordination that's required when you fly out of Vandenberg Air Force Base or Cape Canaveral, and simplify our operations, gives us more flexibility so we can fly more often, we can fly when we want to, and it also simplifies some of the electronics and RF systems that you have to carry on a rocket, because we don't start near Orlando or Lompoc or Santa Barbara. So that's a little bit about the system. You can see the rocket here pictured. You can see the two stages. The upper stage with a big nozzle on it because it's ignited at very high atmospheres. First stage engine's about 75,000 pounds of propellant, of thrust, I should say. The upper stage is about 5,000. Once you're lofted above, you don't need quite as much thrust to get where you want to get to. We're about 70 feet long, and as I said, a little under 60,000 pounds. And so just a few snaps on what we're doing and the status of the program. You can see our first stage engine firing here. It typically fires for about 3 minutes. This is up at Mojave. We do all of our engine testing up there, both for the first stage and the second stage. We do all of our hazardous testing up in Mojave, and we will start operations at Mojave. That's where we'll be flying our first payloads out of. So you can see our engine firing there. The last big firing we did was about 2 or 3 days ago, where we did a nice long 190-second burn. So we're getting full duration burns now out of our system. Our second stage operates for about twice as long, for about 6 minutes, and then has to restart. And we've been going through those burns and restarts and practicing with the system across our engines. You can see some of our structure here up at Mojave. On the left, you can see a liquid oxygen tank. That's in a fixture up there in Mojave. We do cryogenic testing where we take it down to temperature, and then we basically torture the hardware, twist it and pull it and bend it, and make sure that it's going to withstand both the captive carry loads of takeoff and landing, if we needed to, as well as obviously flight and aerodynamic conditions on the rocket. It's got some cork and insulation on the outside and some paint for conductivity because you don't want static electricity to build up on an aircraft. You can see on the right one of our fairings with a payload adapter underneath it being pulled on, so the same kind of thing. That actually happens to be in Long Beach where it's being qualification tested. And so we're in that mode of the program where the design is about done. The qualification testing is in full swing. And so about once or twice or 3 times a week, we go through a major test on the system where we either finish off a main piece of structure or part of an engine, or we vibrate a piece of electronics or shock it. It's an exciting time for the system when you really start to feel and see your struggles and your creations and your sweat creating hardware, creating software, coming together, creating function, and creating a system. And so it's frankly a lot of fun to walk through the factory every single day because it changes about every day. Here's a fairing in separation test, so it's not supposed to sit that way. But this is in mid-separation test, and we've done development tests and qualification tests. So fairing separation, where the front of the rocket separates in flight, is a very, very key event. It's one of the 2 big separation tests that we do. Fairing separation we've completed, and that gives us some good understanding of the shock environment a spacecraft has to be designed for. And then first and second stage separation is the other big SEP test, and that's coming up. Here are some of our electronics. We used to call these boxes, electronics boxes, but now they really look like little flat plates with a bunch of connectors on them. Somehow the electronics has shrunk down to the size of an iPad. The connectors are still the same size pretty much. And those of you who have been around wire harnesses and connectors probably aren't surprised, but they somehow turn out to be some of the most complex little devices that we have. I've had many, many discussions in my career about sockets and pins and connectors and back shells, and I'm sure a lot of you have as well. But really slick, very robust, capable electronics that you can have out in the field. And then these are the kinds of pictures that really get our blood flowing. This is our first rocket out of the factory. At the very end of last year, we created the first rocket. We took it up to Mojave, and you can see the truck that it was put on, and that's in the back of the factory in Long Beach. before it drove up to Mojave. And we took it up to Mojave, and we attached it to a test stand in Mojave by the same 3 hooks, the same positions that the 747 will grab the rocket. And we connected it up to our launch equipment. And our launch equipment is also portable, so the entire system is portable. We have a trailer for locks, a trailer for kerosene, and a trailer for pneumatics. And we rode them up to the rocket, we connected them up, and we went through launch rehearsals. And we had everybody on station. You can see the team on the top right in our little control area. And we exercised the system and went through rehearsal after rehearsal with the team. We actually even had our flight crew there, our pilots, so that they could sit after the system was locked up and loaded, and we could go through a simulated flyout. A little boring when you're not flying an airplane in a simulated flyout, but we went through it because we wanted to understand the timing and the thermal characteristics as the propellants heated up through flight. So really exciting times for us, because with the engines firing, with the first rocket now being produced, having gone through launch countdown rehearsals, you start to really get the sense of the system and the personality of it, and the system is coming to life. And the 400 plus folks on the program are really peeking up and noticing the momentum and what's happening on the system. So a little bit about some of the attributes. The system is kind of unique because of its air launch capability. I was sitting with the Secretary of the Air Force. She came to visit us about 2 months ago and spent some time walking out on the floor, and we were talking about Air Force missions, and she turned to me and she said, "You know, Dan, you can fly out of just about any airport that could handle a 747. And I said, "Yes, ma'am." And so you can think from a DoD standpoint what being able to launch from anywhere might do for space resilience and launch agility. I grew up where there were 2 or 3 spacefaring countries, and there was a Cold War going on for a while, and there was posturing, but it was a pretty well-known quantity. Now I've lost count, but there's well over 20 countries that have satellites, and quite a number of countries are growing launch capability. And so from a U.S. government standpoint, the ability, and those of you who follow space know the idea of resilience, agility, and the ability to operate in space has become very, very important. And from a commercial customer standpoint, the ability to get to orbit, any orbit, is very key. So we'll start out operating out of Mojave. We'll then fly from the Cape on the shuttle landing strip. So we're making our logistical arrangements there, and again, everything is portable in our system, so it's pretty easy to relocate. And then we'll have a Pacific launch site. You want to have these different launch sites because from a flight safety point of view, you can get to different inclinations, different orbits from different launch sites. And then there's a number of other discussions on other launch sites that are active, and we will probably operate from a couple more as well. So just a little bit more of our happy snaps of the system. As I mentioned, it's a pretty exciting time in the factory. Every single part of the system is really moving forward towards first flight, which will happen later this year. And what's really great about working in a Virgin company is there's a tolerance for risk across entrepreneurial space and across Virgin as a company. Richard Branson has led very successful companies, but it's always been leaning forward. And so what we've been able to do is have a program that's very hardware rich, which is really rare in aerospace. And so we're heading up towards first flight with the first rocket, but we have the second, third, fourth, and fifth rocket in assembly right behind it. And so when we go to flight with our first rocket, we'll have the second rocket there on the floor. And we'll have spares from the third rocket. And those of you who have driven teams through development programs know really well what it means to have an extra electronics box, a valve, a stage available to you if you need it. And so, we're We're not a small garage shop. We're a 180,000 square foot factory down in Long Beach that right now is chock full of hardware and a beehive of activity. And I'll just say a couple of more words and then maybe open it up for questions. You know, the key in any aerospace program is the people who are in it. The technologies are wonderful, but they don't happen without the ideas of the people. And the ability to harness the technologies, to mature them, and to drive them through the rigor required to get to an operational system relies on the sense of purpose, the dedication, the imagination, the personal commitment, and the sense of team that comes across the people. And I consider myself incredibly lucky in Virgin Orbit because we have a supremely talented team. And they're attracted by doing something new. They're attracted by doing something new. They're attracted certainly to the brand as well and to Richard Branson's sense of purpose and drive and his philosophies about how to work with people. You know, I mean, Richard's philosophy, for instance, and I'll paraphrase because I won't get this exactly right, but he says things like, you know, train people to where they can leave if they want to, but treat them well enough to where they don't want to. And he says it much better, and with a British accent, which I can't do as well. You know, he has a belief system, and we really work to try to drive those kind of values through the team. We have a team that is really a mix of people who've been in the business for quite a while, like myself, who grew up with satellites and rockets and missile defense systems, people who earlier in their career went to new space companies like SpaceX or Millennium or some of the other spacecraft companies or rocket companies, and then, you know, decided that they wanted to get back into a development mode on a new company. And then a lot of people who are entering the industry, and a lot of people coming out of college or coming from other industries where they've started their career, got the space bug, you know, which is kind of contagious. You know, you may want to get inoculated if you once you leave the room. You'll find yourself working on a satellite in your garage. But it's a really wonderful combination, a really powerful combination, because you have a combination of people who have been through a drive forward through the processes and the disciplines that are required and the lessons learned through space, and people who are asking, well, why do you have to do it that way? Why do you really need to? Couldn't we do it a little differently? Couldn't we? And my job and the challenge, frankly, is to always mix those and stop and make sure you're considering all aspects. And so there's a lot of creativity, a lot of creating new, as well as a lot of understanding of lessons learned, stub toes, scrapes and cuts, and you know, I see a lot of heads nodding, so maybe a couple of people here have experienced those too. So it's great to be mixing those, and then the energy, frankly, from everybody is terrific, because when people, you know, I don't care who you are, you get into a factory or an area where you get to create something new, and it's your baby, boy, the lights go on. So that's a little bit about what's going on in space and how we plan to fit in. We have a manifest that is filling up pretty quickly, and so the commercial world has leaned in first, which is really interesting. It's not the history of space. Historically, it's been kind of government-driven, and then, you know, maybe back and forth a little bit. This is an area in small satellites to where first we're being driven by commercial world realities, and now DoD, NASA, the intelligence community are starting to dive in pretty quickly to say, boy, these platforms being developed, and we can make use of them, and we don't have to have the headache of the development program. You know, how did that happen? So we're on a mission to open up space for everyone. It's one of our main themes, and we're seeing a lot of businesses and a lot of ideas that are enabled by the fact that we can get up and go to 1/4 of the price point that historically has been out there. So let me stop there and open up the floor to see if you've got any questions. The question was what kind of poundage, and I'm going to go to kilograms. But we can put up 300 kilograms to the standard low Earth orbit, which is about 500 kilometers sun synchronous, which means you don't get much benefit from the Earth. If we take a more equatorial trajectory, we can get about 500 kilograms. So, you know, upwards of about the size-wise, it's about 2.5 meters, and, you know, and a fair amount of weight there. The question is, first of all, how much benefit do we get from air launch, and have we considered reusability, or how much reusable is the system? You know, benefit-wise, the attributes of the benefits are altitude, to where we don't have to fight through the lower atmosphere, and so thermal systems and structural capabilities are lower. Our propulsion system can be optimized as well, because we don't have to have our expansion ratios of our first stage and our chamber driven by sea launch, because we're going up from about 35,000 feet. You know, and I don't have an exact number of apples to apples. My guess is maybe on the order of 20% or so benefit there. The other benefits are, you know, as I mentioned, we can get away from the range. We're now governed by the FAA. We're not governed by a launch range, so regulatory-wise, it's an easier, more flexible arrangement. We're trying to get more towards launching satellites the way we would deliver freight from an aircraft, that more like that model. And so those are, and we don't have to do quite the coordination. The ranges, the launch ranges, are getting very, very busy. I think, let's see, General Monteith was briefing at Space Symposium a couple of days ago, and I think he said they're going to have 40, maybe 48 launches out of the Cape this year. I mean, an enormous year for launches, yeah. As far as reusability, I get that question often, and I'll just say a 747 aircraft is as reusable a stage as you can have. So, but to answer the rest of your question, because I know that's not the way you intended it. On the rocket side, we are considering reusability options, and there are a number that we are looking at as we look at forward spirals. Right now, it's 2 expendable stages. But the other side of that equation is manufacturing technology is growing at quite a rate. And at this size, with a single engine on each stage, we have to finish the trade-off between the logistics associated with reusability and techniques like additive manufacturing and the robotics that some of the industries that, like the automotive are bringing forward, that we can take advantage of and do the math and see if there's a real pony in that. The question is, for an abort situation, can we bring back the rocket fully loaded? And the answer is yes. And that is one of the driving cases. Yeah, the question is, can the spacecraft manufacturers take advantage of a reduced environment from air launch? And the answer is yes. And there are some puts and takes on environments, but overall, yes. The question is, why aren't our atomic clocks synchronized? So I'll tell you what I know. And from my experience, and I'm not a timing expert, most of the timing that we get comes from the GPS system, position, navigation, and timing, PNT. And actually those are a constellation of about 24 satellites with a lot of spares. I had the privilege and honor of putting about 12 of those up into orbit recently before I retired from the Boeing company. And so they have, each one of those has an atomic clock, actually multiple atomic clocks on those. And those are the primary source these days for timing across banking, across U.S. government, across most of what we do. And they're pretty darn accurate. Okay, great question. So the question is, with current technology, we have systems like Launcher 1 that are taking off from underneath the wing of a 747. Could a conventional fighter with new propulsion capability or advanced propulsion capability get to space and then get back to a runway? And it's sort of like a shuttle type approach, except not with a big external tank and solid rocket motors. And there are a lot of concepts that are starting to pop up that resemble concepts like that. And there are some advanced propulsion techniques. It's not an easy problem to solve. It's one that's been looked at for many years. I don't know, some folks here may remember or may have even worked on the National Space Plane in the early 90s, I think it was, that was looking at air-breathing engines and then going into more rocket-like behaviors on the propulsion systems. There are advances taking place. There's nothing on the market right now or tremendously far along, but there is a lot of concepts that have popped up. And so I would think over the next 10, 12 years, there will be aircraft that get, if not into space, get close to into space. And there are concepts that we've looked at that others have looked at about taking an aircraft into a suborbital trajectory and then putting a second stage, if you will, to get all the way into space. Chances are, to do useful work in space, you'll always need a second stage, because even if you can achieve the aircraft kind of operation, you often want to go to higher orbits, and so you'll need something in addition to get you there. But it's a great question. It is where there's a lot of work going on, and there are companies that have appeared that are solely working on that. How do you densify the air and the upper atmosphere enough to where you can actually operate and use the air for as long as you can, and then switch to other forms of propulsion. Are we doing just low Earth orbit, or are we considering higher orbits? We are considering higher orbits, and we have some interesting ideas that could get us to geosynchronous orbit or above. What's our recurring cost? I can't share the recurring cost, but I'll share what our price is. Our current price is about $12 million per launch. What's an average flight turnaround time? Without too much stress, about a week. Who will regulate the orbits of the satellites we launched? There's two answers. For the launch license, it goes through the FAA. However, for satellites, most of the coordination goes through the UN, which has the International Telecommunication Union, which really does satellites transmit. And so the big deal on satellites is not having satellites interfere with each other. And so the ITU is a pretty effective body that coordinates frequencies. So the question was about weight and balance of the aircraft as we fly, and how do we address that since we have a rocket on one side. And one of the things we do is we do redistribute the fuel. So is there another department or organization handling people who want to go out for now? So there's another company. And so Virgin Galactic is a company that we actually sprung from. We used to be part of until about a year, 14 months ago, actually when I came on board. And Virgin Galactic, which is centered in Mojave, California, has built a system to put up space tourists into a suborbital space flight where they can go into space and experience the weightlessness of space, look at the Earth from space, and then land right back at the originating site. Where do we stand with electric propulsion on satellites? The technology has been around now for decades, and it is now routinely in use. So I would say most of the satellites that are launched have somewhere in the system electric propulsion, because the efficiency is, compared to chemical systems, is really incredible. And you know, generally speaking, I'm not an electric propulsion expert, but generally speaking, the way electric propulsion works is a gas is used, the atoms are ionized, and then subjected to either an electric field or a combination of electric and magnetic field, accelerated extremely fast out the nozzle, and so the efficiency of the gas is huge. And so you need much less gas. You know, you don't need these huge tanks anymore. You can have a little tank of xenon or something and last you your whole mission. Can I describe the launch maneuver and the flight path angle? Generally speaking, we will climb to about 35,000 feet, and the rocket, what's interesting is the rocket and the aircraft and balancing the system is something that we routinely pass through. So it will, it's not completely fixed in concrete yet, but it's about 35,000 feet. We'll start a bank because we would like to reduce as much as we can the angle of attack that the rocket has to then travel through once it's released. We'll get up to 25 degrees or higher on flight path angle of the 747. The pilot will release, has a switch, will release the rocket. Rocket will wait 4 to 5 seconds and will automatically ignite. So the question is, will we need to condition the LOX during flyout? And other systems use solid propellant that don't have to deal with that. The answer is initially no, that we've sized the insulation on the tanks and the mission profile so that we don't anticipate having the LOX warm up to where the engine would have any problem. As we go forward, there may be some reasons to either vent actively so to keep the LOX cooler, and eventually it wouldn't surprise me, and we've actually outfitted the aircraft to be able to service the LOX so that we could go for very long flights. The question is, first of all, what kind of cooperation do we have with Galactic? And then the other question is, are we at maximum length and weight for the aircraft? So George Whitesides is the CEO of Virgin Galactic. He and I spend quite a bit of time together. We are separate companies, but we do have some agreements to use some resources. Generally speaking, geographically, Virgin Galactic is in Mojave and we're in Long Beach, so there's not a huge amount of crossover. And some of the technologies are different. For instance, they use a hybrid motor, we use LOX kerosene. But we do some, they deal with aircraft activities and regulations, and the FAA, we do as well, and so we certainly coordinate there. We have some common offices, but not a huge amount. But we're always talking and spend a fair amount of time together. We're not maxing out the 747, either in length or mass. There are some dimensions that we're constrained by because there's an engine next to us, and you have to look at ground clearance. But the 747 is a huge lift capability. So, you know, a 60,000-pound rocket is not a lot of muscle strain for a 747. That's used to carrying hundreds of thousands of pounds of payload. Does Mr. Branson have a relationship with Mr. Musk and NASA and others? Richard knows everyone, I think, on the planet. And so I will oftentimes get a call from Richard with, I was just talking to, and how does this sound, or would this work, or does this new technology, you know, is it going to be there within our lifetime? He is always thinking and really travels in an interesting orbit of creative people and leaders in about every industry you can imagine. Has the insurance industry, the spacecraft insurance industry, given our customers a break because of our concept of air launch. We're in the early process of really briefing them and bringing them on board. And so we haven't finalized anything. Mostly for them, it will be about proving out the early launches. And I think, as that goes, I think we will get an insurance break, or our customers will. How did we pick Long Beach? I would say skills and availability. So if you look at Long Beach, just the proximity to other aerospace companies, in El Segundo, in Hawthorne, in Huntington Beach, Downey, you name it. I mean, it's a very rich area, and Southern California continues to be an extraordinarily rich area for aerospace. Boeing just closed a plant in Long Beach, and we take it over. We actually are in a new building that's on old Douglas land. So a lot of the old buildings have torn down, and you see Douglas Park, a huge amount of activity there. And frankly, it's great to be putting an aerospace company on aerospace land. How much different in dollars per pound to orbit do we expect from our system? It's really not for us about comparing dollars per pound. It's cheaper dollars per pound to go on a big rocket because you're an extra customer. If you're a small satellite, you're an extra customer, you're not too much trouble, and there's extra space. So it's actually less expensive to fly on a big rocket. The problem is you can only go where the big rocket is going, and it's usually not where the small satellite wants to be. And so their option is usually to drift for many months to the new orbit, or maybe more likely to not quite ever get to the optimum orbit for their mission. And so that's been the trade-off. And what's happening is most of the new space companies, their business plans don't work with that model. And so they're wanting dedicated service, and they're willing to pay a little bit more to get it. I want to thank you. It's a real pleasure to be here this morning with you. Appreciate all the questions. I appreciate being invited by the museum and looking at that beautiful aircraft out there.
Thank you for watching Peninsula Seniors Out and About. I'm Betty Wheaton. See you next time.